Now, there's the one thing I wanted to show you. So we just went through the derivation of Richardson extrapolation, but you should have noticed that we didn't. You may have noticed that the equation that we used for truncation error was not this equation. So this is the equation that I gave, and this isn't the equation we used. We used a different equation. So what I want you to show you here is how we get from this equation here in the table to the equation that I used. And so the equation in the table is this equation, and the equation that I used is then this equation. Well, it turns out that this is just an alternative representation, but specifically for the composite trapezoid rule, whereas this was just for a single application of the trapezoid rule for one trapezoid. This is a representation for however many trapezoids we're doing. And I can show you that here. As we go through. Okay, so the goal is to get then from here to here. And the way we do that is we say, well, EHI, so that's just the sum from k equals 1 to n of 1 over minus 1 over 12 hi cubed f double prime ck. That's just this equation popped in there. All we're doing is we're just adding up because we're doing a trapezoid rule, so we just add up. We fit one trapezoid, then we fit another trapezoid, and we have some error for each one, and so we have to add E1 plus E2. We have to add up all those errors. So that's all we're doing here. For all the segments that we have, we add up the error. So that's equal to minus 1/12 hi cubed times the sum of f double prime ck. And again, this is the second derivative at some intermediate point ck on the interval between a and b. Now we can define this f bar double prime, and that is going to be approximately equal to, so f bar double prime, what that's going to mean is that's going to mean the average value of the second derivative over the entire interval. And that's going to equal approximately equal to the sum of all the second derivatives evaluated at each point that we have divided by n. Okay, so then we can take this, and we have this sum of f double prime ck. We have that in our equation here. Okay, so then we can just substitute. We can rearrange this and solve for this. So we do that. So this is equal just to nf bar double prime, and then we just put nf bar double prime into our original equation for that value, and we get EHI is equal to minus 1/12 hi cubed and f bar double prime. So having done that, then we just recognize our hi is, so I'm going to try to get this n out, and this n should have a subscript I on it. I'm trying to get this n out, and so I can just substitute. I know that hi, this is just the definition of our step size, is equal to b minus a over n, because we have equally spaced intervals, and so that means I can just move the n over here, swap places the n and h. You can think of it that way. So n is equal to b minus a over h. So I just sub in then b minus a over h in for n, and this is the equation that comes out. B minus a over h is put in for n. That's the only difference between these two equations right here. And so that's it. And if you see here, hi cancels with this, so we cancel with one of those, so that becomes hi squared. So we have minus 1/12 hi squared bi minus ai times f bar double prime. And so we've done it. We've gone from what we started with, the error for just one instance, EHI is equal to minus 1/12 h cubed f double prime c, and we've then come up with the error for that we used in the other formula.